Hello, today we will be learning about GCD, LCM, prime factorization, and the Euclidean algorithm. Prime factorization. The fundamental theorem of arithmetic states every integer greater than 1 can be expressed as the product of some prime numbers. We call this product the prime factorization. As we can see here, we can write 72 as 2 times 36. We can then write 2 times 36 as 2 times 2 times 18. We can then write 2 times 2 times 18 as 2 times 2 times 2 times 9. We can then write 2 times 2 times 2 times 9 as 2 times 2 times 2 times 3 times 3. Since all of these numbers are primes as their lowest form, we call this the prime factorization. GCD. GCD is the greatest common divisor, also known as the greatest common factor. Finding the GCD is just finding the largest number that divides both numbers. As we can see here, we are trying to find the GCD of 24 and 18. If we find the prime factorization of both numbers, we can see that this 2 is shared by both, meaning that they are both divisible by 2. And right here, we can see that these two blue 3s they both are divisible by 3, and we can see that we are just left with two 2's and a 3, meaning that they don't share any more common factors. So the GCD of 24 and 18 is 6, or 2 times 3. The LCM, also known as the least common multiple, is the least number that divides both the numbers. So if we were trying to find the LCM of 6 and 21, we'd first find the prime factorization. So 6 is equal to 2 times 3, and since 2 and 3 are both prime, that is a prime factorization. And 21 is equal to 3 times 7, and since 3 and 7 are both prime, that is a prime factorization. And to find the least common multiple of these two numbers, we just take the greatest power of the primes of both numbers. So right here, we would need a 2, since if there isn't a 2, then 6 would not be fulfilled. And we'd also need 3. And since we already have a 3, we do not need the 3 in 21. So we only need the 7. And 2 times 3 times 7 is equal to 42. So the LCM of 6 and 21 is 42. Divisibility trick. For a number to be divisible by 2, it must be even or end in a 0, 2, 4, 6, or 8. For a number to be divisible by 3, the sum of the digits must be a multiple of 3. An example of this is the number, let's say, 719. The sum of the digits would be 7 plus 1 plus 9, which is equal to 17, and 17 is not a multiple of 3. For a number to be divisible by 4, the last two digits must be divisible by 4. So if we have the number 4,884, we know this number is divisible by 4, since 84 is equal to 4 times 21. For a number to be divisible by 5, it must end in a 0. So 105, or let's say 200, are both divisible by 5 since they end in a 0 or a 5. For 6, it just must satisfy the divisibility trick for 2 and 3. For 8, the last 3 digits must be divisible by 8. So basically that means if we have the number 100,800, we know this is divisible by 8, since 800 is just equal to 8 times 100. For a number to be divisible by 9, the sum of the digits must be a multiple of 9. So let's say the number 819. 8 plus 1 plus 9 is equal to 18, and since 18 is equal to 2 times 9, we know 819 is a multiple of 9. And for 10, it just must end in a 0. So if we have like 330 or just 50, we know these are both multiples of 10. For divisibility by 4. So let's start out explaining how numbers are written in base 10, which is what we use. So let's take the number 385, for example. 385 is broken into 3 components, which is 3 times 10 squared plus 8 times 10 to the first plus 5 times 10 to the 0, which is just 1. So we can see that 10 squared is actually divisible by 4, since the prime factorization of 10 squared is equal to 2 squared times 5 squared, and 2 squared is 4. So that means 3 times 10 squared is divisible by 4. So let's take a larger number, for example. Let's say 23,456. We can rewrite this number as 234 times 10 squared plus 5 times 10 plus 6 times 1. So this term right here we can see is divisible by 4, since 10 squared is divisible by 4. So we are just left with the last 2 digits. And if that is divisible by 4, then the whole number must be divisible by 4. Proof for divisibility by 8. We'll be using the same concept as proof for divisibility by 4. So again, let's take a large number such as 5,824. We can write this as 5 times 1,000 plus 824. And since we know 1,000 is equal to 2 cubed times 5 cubed, since 1,000 is 10 cubed, we know that 5 times 1,000 must be divisible by 8, since 8 is just 2 cubed. So let's take another large number such as 25,620. We can again write this as 25 times 1,000 plus 620. And since we know this term right here is divisible by 8, we only need to check the last 3 digits, or these numbers. Proof for divisibility by 2 to the n. If you haven't noticed already, the numbers we've been using are in the form of 2 to the n, since 4 is equal to 2 squared and 8 is equal to 2 cubed. We use this since in base 10, we write everything in the form of a sub 1 times 10 to the n plus a sub 2 times 10 to the n minus 1 plus a sub n times 10 to the 0. Since we know that 10 to the n is equal to 2 to the n times 5 to the n, all terms after this 10 to the n are divisible by 2 to the n. So we only need to worry about the last n terms. So let's say we want to find the divisibility trick for 32. So let's take a large number such as 1,234,567. We only need to look at the last 5 terms, since 2 to the 5th is equal to 32, and we're trying to find the divisibility trick for 32. So we can just rewrite this as 12 times 10 to the 5th plus 34,567. And since we know this term is divisible by 2 to the 5th, since 10 to the 5th is equal to 2 to the 5th times 5 to the 5th. We only need to worry about the last n terms. Divisibility by 3 and 9. Again, using base 10, we can write our number, let's say 316, as 3 times 100 plus 1 times 10 plus 6 times 1. We can now see that we can write 3 times 100 as 3 times 99 plus 1 plus 1 times 9 plus 1 and plus 6 times 0 plus 1, but the 0 doesn't really matter. So we can now expand this as 3 times 99 plus 3 times 1 plus 1 times 9 plus 1 times 1 plus 6 times 1. And we now know that since 99 is divisible by 3 and 9, this term is already divisible by 9. So we don't need it anymore. And now we're just left with 3 times 1. And we can again see 1 times 9 is divisible by 3 and 9. So this is essentially, we don't need it anymore. And we're just left with 3 times 1 plus 1 times 1 plus 6 times 1, which is just the sum of the digits. If we make this into a more general idea, we can just write any 10 to the n is equal to 9999, or this is the n minus 1 nines plus 1, and since this 9999999 can be both divisible by 3 and 9, because it's basically just, if we divide by 3, it's just 3, 3, 3, 3, 3, or there's n minus 1 threes and 1, 1, 1, 1, 1, 1, 1, or there's n minus 1 ones. We basically just get 1 times the digit, which is essentially just summing up the digits. The Euclidean algorithm. The Euclidean algorithm states that the GCD of A and B is equal to the GCD of A minus B and B if A is greater than B, and the GCD of A and B minus A if B is greater than A. This is really helpful when trying to find the GCD of very large numbers. So we'll use this example. So we're trying to find the GCD of 910 and 231. So the GCD of 910 and 231 can be expressed as the GCD of 910 minus 231 and 231. This is equal to the GCD of 679 and 231. We'll repeat this process and we get the GCD of 448 and 231, and we'll do it again and we get the GCD of 217 and 231. Now that 217 is less than 231, we'll use our alternate Euclidean algorithm and we get the GCD of 217 and 14. So now if we keep on repeating it, we just get the GCD of 7 and 14, which is just 7. So the GCD of 910 and 231 is just 7. Finding the number of factors. So there's a simple theorem that can just find the number of factors of a number. It looks very confusing at first, but it's quite simple. So we'll start off with an example. How many ways can you choose an outfit that consists of a t-shirt and pants if you have 5 t-shirts and 4 pants? It's really easy to see that there's 5 ways to choose a t-shirt And for each of those 5 t-shirts, there's 4 pants that correspond. So it's just 5 times 4. So now, well, the theorem to finding the number of factors of, let's say, k, if k, using the fundamental theorem of arithmetic, k is equal to p sub 1 to the n sub 1 times p sub 2 to the n sub 2 times p sub 3 to the n sub 3 to p sub n to the n sub n, where p is essentially just all the primes. So now the theorem states that the number of factors is just n sub 1 plus 1 times n sub 2 plus 1 times n sub 3 plus 1 times n sub n plus 1. So now we'll use an example. We'll try to find the number of factors in 100. So 100 we know is just 10 squared. And 10 is equal to 2 times 5. So 100 is essentially just equal to 2 squared times 5 squared. So now if we go back to our theorem, it states the number of factors of 100 is just 2 plus 1 times 2 plus 1. Since 2 is just the exponent, and we're essentially just adding 1 to the exponent and multiplying all of them together. So the number of factors of 100, 2 plus 1 times 2 plus 1, which is just equal to 9. So now for the proof. We can see the number of primes that divide. Well, we can see that all factors of 100 can be written in the form of 2 to the n times 2 to the k, where n is between 0 and 2, and k is also between 0 and 2. And n and k are both integers. So for the number of integers that satisfy this, we can see is just 0, 1, and 2, which is just 3 integers. And since whatever, using our example from before, 5 times 4, we can just use 3 times 3, which is just 2 plus 1 times 2 plus 1, which is equal to 9. A handy tip. So the GCD of A and B times the LCM of A and B is equal to AB. So let's call A equal to P sub 1 times N sub 1 times P sub 2 times N sub 2 to P sub N times N sub N, and B equal to P sub 1 times N sub 1, P sub 2 times N sub 2 to P sub N times N sub N. So basically the GCD of two numbers is just what is in common of those two numbers, and the LCM is basically just what's uncommon. So if we add the uncommon and the common, we're basically just getting the whole set. So let's just choose two numbers. Let's just say 20 and 50. So the GCD of 20 and 50, we just first find the prime factorization. 20 is equal to 2 squared times 5, and 50 is equal to 5 squared times 2. So what the GCD is basically just saying, it's like the lesser of the two, so which is just 2 and 5. And then the LCM is just stating it's like the greater powers, or like the uncommons, and it's just 2 squared and 5 squared. And now if we multiply this together, we can just see it's just 2 squared times 5 squared times 2, which is just 20 times 50. So now we'll try to work through some problems. Find the number of factors of 51,840. So this problem looks very tough at first since it is a very big number, but we'll first try to find the prime factorization. So 51840 we can quickly see that this is a multiple of 10 since it ends in a 0. So we know this 10 times 5184. So now we can see this number is divisible by 4 since it ends in an 84 and we know 84 is divisible by 4. So then if we divide this by 4, 5184 is equal to 1271. So this is just equal to 4 times 1271. Wait, no, that is not right. It's just equal to not 1271. It's 1296. Okay, so now we know 1296 is divisible by 2 again, or actually it's divisible by 4 since 196 is divisible by 4. So 1296 is equal to 4 times 324. So now again we can see this number is divisible by 4. So we call 324 is equal to 4 times 81. So now 4 times 81, well 81 is just 9 squared. So we can essentially just call 51840 equal to 10 times 4 cubed times 9 squared. And now if we break this into prime factors, this is just equal to 2 to the 7th, since 4 is equal to 2 squared, and 10 also has a factor of 2, times 3 to the 4th, since 9 is equal to 3 squared, times 5. So now we know, using our theorem, the number of factors is just 8, since that's 7 plus 1, times 5 times 2, which is equal to 80.
Prove 199 is prime. If you're trying to prove a number is prime or find the prime factorization of that number, you only need to test the primes that are less than or equal to the square root of n. We know this since square root of n times square root of n is equal to n, and let's say we test a number larger than square root of n. That means the number we're multiplying it by must be less than square root of n, and since we must have already tested that number, we only need to test the numbers less, the test the primes less than square root of n. So 14 squared is equal to 196. So we basically only need to test the primes that are less than or equal to 14. So those primes are just 2, 3, 5, 7, 11, and 13. So we quickly see that it's not divisible by 2 since it's not even. It's not divisible by 3 since 9 plus 9 plus 1 is 19, and 19 is not divisible by 3. It's not divisible by 5 since it doesn't end in a 0 or a 5. Now, let's see if it's divisible by 7. So, 7, 199, 2, 14, 59. 59 is not divisible by 7. So let's try 11 now. 11, 199, 89. 89 is not divisible by 11, so we just need to test the last number, 13. 13, 199, 13, 1, 69. 69 is also not divisible by 13. So if we test any prime greater than 13, well, greater than 14, it must have been multiplied by a prime that is less than 14. And we already tested all the primes less than 14. So 199 is prime.